The mass number is not the same as the atomic mass, the mass of an atom. The mass number is the number of protons and neutrons in one isotope, but the atomic mass is actually an experimental number determined from all the naturally occurring isotopes. A simple average is what you're accustomed to doing. You just add everything up and divide by the number of things. Well, it's hard to do with atoms because they're so tiny and there's so many of them. And so what we do instead is we use a weighted average. And that takes into account the fact that we don't have equal numbers of all of the objects. So we calculate a weighted average by multiplying the percentage of the object as a decimal by its mass for each object and adding the numbers together. And that probably made absolutely no sense at all. The number of isotopes, so like hydrogen has 3 isotopes. They are not in equal numbers. It's not a third of hydrogen is one and a third is the other and a third is the third one. That made a lot of sense. It varies from element to element, but the percent natural abundance is the same pretty much no matter where you got a sample of hydrogen. So the percent natural abundance is the relative amount that is found in a given sample. So there's the picture I was looking for. Here's an example for neon. A sample of neon, and that's the gas that's in this sign that's making that bright orange color. A neon sign actually has neon in it. So 90.48% of the neon is this isotope, the neon 20, with 20 protons and neutrons together. 9.25% is the green one, neon 22, and 0.27% is neon 21. So these are the natural abundances, and those are determined experimentally. You don't figure them out from the periodic table. You don't memorize them or anything like that. So we use a weighted average, and here's the example for copper. Copper 63 has a mass of 62.930 atomic mass units. We haven't talked about those, have we? It's a unit for measuring atomic mass. Isn't that a clever name, atomic mass unit? 69.09% abundance. And the other isotope, 65, has a mass close to 65 and 30%, 30.91%. So to calculate the average mass, we take this percentage, we divide it by 100 to make a fraction out of it. So 0.6909, and we multiply by the mass of that isotope. And so that is the amount of mass contributed by that isotope. And then we add the percent divided by 100 times the mass of the other one. And we add those together. There could be 3 or 4. And we come up with the average mass. And just like we can talk about, well, this is normal behavior for a human, but actually, is anybody normal? There's probably no one person that's normal, right? But we have this idea of what's normal. So this is an average mass, but no one atom of copper has that average mass. We're okay with that, though, because we never deal with just one atom of copper. We're usually dealing with bazillions of them. And so the average mass is what's important. Okay, so we're going to have to finish the rest of this in the activity session, and we'll work on the worksheet about this stuff.